Okay, thank you very much for the kind introduction. Also, thank you to all the organizers for the work during the week and prior to the conference. And I'd also like to thank my co-authors, Yuming Zhao from University of Waterloo, IQC, and Broadbent at the University of Ottawa. So first, I just want to motivate what problem we're trying to solve here. Okay, so imagine some distant point in the future, we finally have access to fully fault-tolerant quantum computers, but they're expensive. It's largely over the cloud, and here we have some classical client, totally bewildered. How do they navigate this landscape, interact with these servers, and get answers to the questions that they want to ask? So a little bit in more detail, you have some client, they might have some circuit they want to run, they have their computation, they can send a description to some server over the cloud, they get a response, but they need to be convinced that that's the correct response. How do they know the server ran the circuit they wanted on the input they chose? How do they know they got the right measurement result? And they're sort of at an impasse, it appears, because since they're classical, they can't really make predictions of what the outcome might be. So protocols for verifiable delegation are all about, let's find a rule of interaction between a client and a server, or maybe multiple servers. So at the end of the day, when they get the result, if it's correctly done, honest behavior, they'll accept with high probability. And if there's deviation from the correct behavior, then they'll reject with high probability. So that's the idea. I also want to add a different concern, this time from the point of view of the server. So the technical term is a zero-knowledge proof. But in this case, it's kind of simple. Suppose an honest server wants to convince their clients that they have the result of the computation, so they want to run one of these protocols. But they might be worried that while running one of these protocols, they might reveal inner workings of what they do. So maybe they have some proprietary quantum algorithm, and they're producing these certificates at the end of the protocol over and over. And like, can the client slowly reverse engineer trade secrets of the company? So these are the two goals. We want to solve both of them at the same time. We want zero knowledge and verifiable protocols for delegating quantum computation. So we'll look at what's been done previously. I think you can largely group them into three categories of previous protocols. So first, we have these protocols where you have a classical client and a single quantum server, but the classical client needs access to some amount of trusted quantum functionality, like something like preparing a single qubit state and sending it over back and forth with the server. So I mean, it's fantastic we have protocols like that, but if we're especially suspicious of quantum functionality, then it's not really device independent. So the other protocols, thanks to Ilya in the previous talk, we have some idea of how they work, but in this setting, we have some computationally bounded server. And there's these ingenious protocols where we weave in these cryptographic challenges into the back and forth, and you can verify computation like that. But then the downside is you have some. I mean, is it a downside or not? But at the end of the day, you have some hardness assumption, kind of like the debate on Tuesday. So it's like the client might be worried. Maybe these problems aren't that hard, or maybe there'll be a small incremental improvement or a dramatic improvement, and they don't know, right? So this is sort of like not fully device independent. We know how to do it fully device independent as well. So in this setting, you have the only way we know so far, and likely ever, will be involving a single client, classical client, interacting with two or more quantum servers or provers. And there's a caveat with this approach as well. These servers can't communicate during the protocol. You want to cross-interrogate them and then build confidence like that. So the spatially isolated, really, it's about not communicating. So I mean, it's a little, how reasonable is that for a client to enforce, even in this distant future? And it's also expensive, right? In the case I'm imagining, these servers are difficult to run. You don't want to use two servers when one server will do to do the computation. You're doubling the compute power you might need. And for zero knowledge, actually, prior to our work, so there's a wonderful transformation by Grillo, Yuan, and Slofstra, and they show that any multi-prover protocol can be made zero knowledge, you transform it into one, but you get up to 6 provers now. Okay, so it's like, okay, 6 now is even worse. This is crazy. Maybe we can do better. So this is our model. So our model doesn't fall into exactly any of these 3 categories, So we're going to envision a single powerful quantum server. It's going to do all of the heavy lifting, okay? That's the one that's going to need to be expensive. There's going to be a second quantum device, okay? So we're still using non-locality and isolation. It's going to be more generic, more rudimentary, and it's all going to be done in a single round, okay? So we'll take a first pass at how it works. So suppose a client wants to delegate some computation. They have some circuit they want to know the answer to. There's going to be this setup phase. So they're going to purchase this off-the-shelf, should they device as a type, so off-the-shelf device based on X. So what am I calling an off-the-shelf device? I'm saying this thing is generic, okay? So there's some computation the client wants done, but the workings of this device don't depend on what that computation is, just on the size. That's like absolute X, how much compute they need. So they purchase, you know, in fact, they could just buy this device ahead of time. They don't even know what they're going to compute. They just go and pick this up from, you know, the service provider that has the cloud, the expensive quantum computer, is supposed to share an entangled state with the server and can measure like a constant number of qubits on some n qubit register. Okay, and once they have this device at some later point, they'll have their computational task, and then they're going to play a game. They're going to do verification. So they're going to send a question over to the server. They're going to receive some response. They're going to push some buttons on their device and cross-reference and check and decide whether to accept or reject. Okay, so one thing, maybe two things to point out. One, to underscore again, we still need isolation during this protocol, the device and the server. Okay, another thing, this statement, this genericness of this off-the-shelf device, this is only assumed for honest behavior. We're saying we're looking for protocols where honest behavior can be conducted in this manner, can be satisfied. Dishonest behavior, we imagine maybe the companies, you know, they deliberately make a malicious state for a particular client on a particular circuit, and the box they give is actually powerful as well. That's fine. Like, these protocols are going to be sound against that. We're making completeness more strict, maybe a step towards something more reasonable. Like in this cartoonish example, it might not end up, you know, being able to be instantiated like that, but it feels like maybe there's more control over this device you get. Maybe enforcing isolation is now a bit more doable. Okay. So let's take a second pass, just a little bit more detail. So here I'll say that the device, the honest device, is purported to measure up to 6 qubits. But dishonest device, we're still going to use device-independent techniques. And here it's off the shelf, meaning the entangled state. It only depends on the size of the problem. So how can we do it? The client picks up the device. Okay, they have some computation. Really, they're going to be thinking about, they're going to look at the corresponding Hamiltonian. Now their decision problem is really about the ground energy of some Hamiltonian. And here, this little comic, this is the, you know, purported honest behavior. The server pre-shares entanglement, of course. Why not? Enough entangled EPR pairs with this off-the-shelf device. And then during the game, the verification step teleports the ground state corresponding to the computation that needs to be done. And then the device can make measurements, right? And 6, in the proofs for zero knowledge, we have these 6 local Hamiltonians. So basically, this device can measure a term from the Hamiltonian. And then, okay, so they can accept or reject. So before getting to techniques, let's just talk about what we can do. So all efficient quantum computation has verifiable delegation protocols in this model we show, and it's zero knowledge as well. So that's one result. As a corollary, so like I said, we're making completeness more strict. So really, this is like a special type of a multi-prover protocol. So we sort of settle this implicit open problem in the community. So I talked about this 6-prover zero knowledge for MIP star, at least for QMA. Basically anything that a quantum computer that would be trusted that could efficiently be verified, we can do that too. So every language in QMA has a 2-prover, 1-round zero knowledge proof. So that wasn't known. And I think it's like sort of like maybe the end of a long story of improvements of this path, getting less rounds, less provers, adding zero knowledge, things like this. And then just a little disclaimer, if anyone has seen the preprint out there, so there's a little bit for the experts, but we had inverse polynomial completeness soundness gap in our results, but we now know how to get constant completeness soundness gap with respect to just this corollary, and it'll be updated in a later version. Okay, so you know what's technically difficult about this? So here's the comic. This is the honest. This is what's supposed to happen, right? EPR pairs teleporting a state. This is difficult from both the verifier and the server's point of view. The verifier needs to certify there's EPR pairs. Okay, so we've seen this self-testing. You know, we know there's techniques to violate a Bell inequality, get EPR pairs. Okay, we need many EPR pairs. There's techniques for that too. Okay, but we need many EPR pairs, but the device can only measure 6 of them. Okay, so now it's getting a bit more strict. You want to certify an arbitrary amount of EPR pairs, and one of the devices can only measure, you know, and it's in the honest implementation, it should only be able to measure 6 qubits. Okay, so we'll talk about solutions to this. There's another problem. Okay, zero knowledge. Okay, the honest behavior, the server just gives the entire ground state to some device that can measure with respect to terms of the local Hamiltonian. So even if you're not an expert in zero knowledge, like, okay, no, I'm not really an expert in zero knowledge for working at this at least, it seems suspicious. How are you going to keep anything secret? You just teleported the entire ground state over and they can just start making measurements, right? Okay, so these are the two obstructions I wanted to share. So how do we overcome them? The first is improvements in self-testing. So there's some self-testing results out there that you could self-test for, you know, they're great results. You can self-test for a lot of entanglement using constant, measuring a constant number of qubits. So we needed something stronger still. We needed something that has completeness 1, where honest behavior is always accepted. So we introduced a new self-test called the low-weight polybraiding test. We show that it can self-test robustly and EPR pairs, and it only requires 6 qubit measurements. And in fact, this all-powerful device, it only needs to measure 12. And we could get them smaller, I think like 2 and 4, but this is the idea. So we needed this to be having completeness 1. So this is the first game that has those properties we needed. Here's slightly more technical. I'll try to be brief. How do we deal with the fact that the whole ground state is being teleported over, right? So it's an extension of some simulatability results by Broadbent and Grillo that also plays well with self-testing. So the idea is for any language in QMA, there's a family of verification circuits, a very particular family of verification circuits, and they satisfy 2 properties. The first thing is, if we look at the corresponding Hamiltonian, it's something called XZ type. That just means all of the terms are tensor product of X and Z. These are the type of operators we normally are able to self-test. Although we can self-test others, a lot of the literature is about X and Z. Okay, so we can get that. The second property is a little bit more technical. It's saying, suppose we have a yes instance, and we look at a small slice of all of the n qubits, 6 or less, then the reduced density of the ground state, if we trace out all but those 6, then that can be obtained in polynomial time, actually classically. Okay, so there's just a simulator that can output a description of that, you know, some precision of the entries. So what does it mean? It means that the measurement result the verifier gets in the interaction is something they could have computed themselves. They don't learn anything, okay? But how are they convinced of correctness? Because they get an entire state teleported all at once, and that means they know there's some sort of quantum data consistent with these small snapshots. And just knowing how to compute these small snapshots, that's not going to convince them because they don't know, is there a quantum state that looks like this, looks like this, looks like this? Okay, so this is the second technical. Third, okay, too technical. There was no informal statement of this available. A bit for the experts, but I'm a bit proud of it, so I'll tell you. So the self-testing to weave this first result with the second, we needed an advancement in something called approximate representation theory. So we prove an enhanced version of Gauer's Hatimi theorem from approximate representation theory. So modern techniques in self-testing are really using group theory, group presentations, approximate representation theory, and this is like the cornerstone stability result in the field of how you take almost winning strategies to telling you, a neighborhood about where the operators are living, and then you get the state. Okay, but actually we needed a stronger version of this to deal with some technicalities. And I think it also illuminates, actually, if you go back and you look at other self-tests, they're like a little bit easier to understand, in my opinion, with this new version as well. Okay, so I think that's mostly all I wanted to say. I can end on some open problems, things I'm generally interested in this area, not just about low-weight polybraiding. The first, I think, is like the elephant in the room. It's like, why is there 3 talks on device independence? We have this huge, great conference. The biggest problem is they're not noise tolerant nearly enough. We have this thing like robustness, but robustness is like, doesn't really map on with what you think it should mean. And so we have some encouraging, vibes from the low-weight polybraiding test. So you take this canonical test for many EPR pairs, polybraiding test, one of the best out there. You should play it with friends. Yeah, the problem is if you look at a noise model where you have constant noise on each EPR pair, then the players will just get killed. They'll lose almost certainly, right? You make these big measurements in this game. You measure like all n qubits sometimes for some questions, right? And the errors just accumulate like that. So in low-weight polybraiding, we don't have that, at least, okay? So we can tolerate, they'll still win with decent probability if they're honest but noisy. But then, yeah, I mean, it's not surprising. We didn't resolve this. We weren't trying to. There's a really hard problem, I think. But it's not robust enough now. Now our game's a little bit less robust than polybraiding. So what that means is, asymptotically, eventually dishonest behavior will be able to outperform noisy but honest behavior. And since I'm a theorist, I don't know when those switch over from one another. But it's just like, okay, these are encouraging flavors of things that we might do. I think ultimately we need to rethink self-testing at a higher level, a more generic level. But I think it's a great question. So something I'm interested in. Here's some complexity theory, like, okay, so if you call it a complexity class, we get QMAs in this class. And is it actually equal to MIPS? How big is it? So I was talking with Henry and Thomas about this at various points. And they both said that if you don't have this small measurement, just this genericness of the state being independent of the problem instance, probably it's MIPS star. And then with the restriction, neither of them really had a guess. It's like, okay, it's not clear. Okay, and some more, but maybe I won't go into that. Maybe I'll just take questions from the audience. If you think that point is interesting, you can ask it again. But thank you for your time.
Right, thanks for the talk. I already see a first question here.
Yeah, so I have two questions. First question is about soundness of your construction. So if prover knows which 6 qubits of the history state is teleported, he can break the soundness. So how this is avoided?
Yeah, the other prover doesn't know. I'm not sure what your question is. I mean,
yeah, so I think the soundness is, so only 6 qubits are teleported to the verifier? No?
The entire ground state is
entire states are teleported.
Yeah, you would be right. If you only teleported 6, then you can't get soundness anymore.
Okay, but in that case, how can you guarantee the zero knowledge if entire state is sent?
Yeah, that was the point of the dilemma that I was showing. Like, it's surprising. You shouldn't be able to do that intuitively, but due to great work prior to ours by Broadbent and Grillo, and actually Grillo, Yuan, and Slofstra around the same time using similar techniques, we know that, yeah, you can get zero knowledge in these settings. You can reproduce the transcript. And so this is a wonderful story. I recommend checking it out if you're wondering how you get this. Yeah.
The other question is, so James Bartzek also constructed NIZK with a setup model where bell pair is transmitted. Maybe if you attended his talk, he presented construction of NIZK, non-interactive zero knowledge for QMA, by assuming that some trusted center can distribute bell pair. And this somehow looks like this setup. So how they are different?
Yeah, I wish I knew. Maybe I can speak with him at a later point. Like I said, I'm not coming more from the pure math side than the crypto side. And so I'm always excited to see if there's a similar flavor of these results elsewhere. Yeah.
Okay, thank you.
Okay, do we have more questions? I have one, actually. I'm not sure I fully got what the capabilities of the small untrusted device have to be. So I understand it's limited in how many qubits it can measure, but does it have to store qubits?
Yeah, so usually the group of people that work on this analysis don't really think about memory or a time frame. But yeah, there's going to be time steps. Questions are sent, information is received, and so it'll have to store the ground state long enough for the verifier to, yeah, it at least has to store the EPR pairs, of course. Yeah, I would say that, yeah.
And so it has to have some quantum memory?
Yeah.
And is it reasonable to assume that it has to be able to store quantum states, but is restricted on the measurements?
So the measurement restriction, the size, I think that's like it plays well with the zero knowledge, because like if you start making too big measurements, that zero knowledge can be compromised, and it's like, why not make it as strict as the math allows you to? But I think it's like more extreme than restricting its computational power. The point is, it's not a quantum computer. It doesn't have to be. It could be, and it's still sound, but it doesn't have to be. Like, what if you could get just 2? Wouldn't that be cool? Like, how small can you get it? It's like, what's the smallest your cross-check needs to be to verify all computation? Like, and that's, so we at least got it down to 6. Maybe you can get it down to 3. That'd be pretty cool. I don't really know. Yeah.
Okay, thanks. Any other questions? Okay, I don't see any more questions, so let's thank our speaker.